Okay, so we are now going to start the exercises of this section. The first few ones are just going to be done by substitution, but anyway, let's just go through them. So the first one here, we have to calculate limits, of course. The first one is this limit, which from the results we have seen in this section, it comes like this, the answer. So it is just 2 times minus 7 plus 5. So that means minus 14 plus 5. That is minus 9. Next, the next one is this, limit x tends to 3 of 10 minus 3x. We are able to substitute like this to find the limiting values because these expressions are polynomials, and we have already seen in this section that for polynomials we can do this. So that's why we are justified in doing this. That is 10 minus 9, this is 1. Then 3. The third one is limit x tends to 2 of minus x square plus 5x minus 2. Ideally, while writing the solution, you should write the thing that because polynomial functions can be, for them limits can be evaluated by substituting, that's why we are able to do so. But because we have to do it again and again, so I quit that writing part. Minus 2 is equal to minus 2 square plus 5 times 2 minus 2. This is minus 4. Minus 4 and minus 2 give us minus 6, and this is 10. So 10 minus 6 is 4. Then the fourth one, it keeps getting longer. X tends to minus 2 and the polynomial is x cube minus 2x square plus 4x plus 8. We have x cube minus 2x squared plus 4x plus 8 equal to, oh, this is minus. See how easy it is to make mistakes. Minus 2 whole cube minus 2 times minus 2 whole square plus 4 times minus 2 plus 8. So we get minus 8 minus 2 whole square is 4. 4 times 2 is 8. That means another minus 8. Then again from here also we get minus 8, and the last term is plus 8. So these two cancel each other and we are left with 2 minus 8s. That means minus 60. Next, 5. Okay, the fifth one is limit as t tends to 6. Here the variable is t and the function is 8 times t minus 5 times t minus 7. Minus 7 equal to, this is also a polynomial, because if you multiply the terms out, you do everything and then you do the calculation, then you get a polynomial. So here also that same substitution rule can be applied, and that gives us this limit, 6 minus 5 times 6 minus 7. 6 minus 5 is 1, 6 minus 7 is minus 1, so the answer is minus 8. Then 6. The sixth one is limit as s tends to 2 over 3 of what? 3s times 2s minus 1. 3s times 2s minus 1. Here also the function is a polynomial in s. So we have three s times 2s minus 1. So if you do the substitution, you will get this. See, if you find it somewhat difficult to understand, it may happen that you are finding it difficult to understand that we are substituting s equal to 2 over 3 in this expression itself, although the expression itself does not look like a polynomial. If that is the case, then you can multiply the terms out, and instead of this you can do one more step where after writing this part of the symbol, then you write 6s squared minus 3s, because then by definition it looks like it is a polynomial. Then you can substitute s equal to 2 over 3. But we have just simply done that itself, but we have skipped one step. Truly speaking, we have skipped one step. So if you find it a little uncomfortable, you can add that step. So what are we getting finally? 2 times 4 over 3 minus 1. So 4 over 3 minus 1 will means 1 over 3. So that means the answer is 2 over 3. Then 7. The seventh one is limit of x plus 3 over x plus 6 as x approaches 2. Okay, now here this is no longer a polynomial, but this is a rational function. But for such functions also we have seen how to calculate limits. Rational functions are quotients of polynomials and their limits can be calculated at some point, provided that point when you substitute in place of x in the denominator polynomial, the value is non-zero. If that happens, then we can substitute, and that is the case here. If we write 2 in place of x, then we get 8 in the denominator. That is not 0. So that's why we have, by that other result which involves limits of rational functions, we have this. Two plus 3 over 2 plus 6. That means the answer is 5 over 8. Next, 8, and the 8th one is limit of 4 over x minus 7 as x approaches 5. Four over x minus 7. Note carefully that this is also a rational function. The denominator is a polynomial, it's a linear polynomial. But the numerator is also a polynomial, it's a constant polynomial. And if you substitute 5 for x, the denominator does not become 0. So that's why we can do our usual stuff and calculate this limit like this. 5 minus 7. So 5 minus 7 is going to give us minus 2. So that means the answer is minus 2. That's it. It is highly suggestible that you do one more thing, although it has not been said in the text. But I want you to draw graphs of these functions. That is, you go to that site, Desmos Graphing Calculator, or if you have a personal grapher, that also you can use. You go there and, for example, you draw the graph of y equal to x plus 3 over x plus 6, and then see what is happening near the point x equal to 2. You will see that there the y value is close to 5 over 8. Well, in this case it will be actually equal to 8 because 2 is a point in the domain of this function at which its value is 5 over 8. But as we have already seen, for some functions that is not the case, that the point where we are calculating the limit of the function may not be a point in the domain of the function, but still limits exist. We have already seen many such examples. So for such examples, looking at the graph is very illuminating. Here also you can look at the graph and see exactly how things are changing, because if you just look at the function and you are just doing things algebraically, symbolically, but still it may give you a better idea if you look at the figure. Okay, so let's see the next one. The next one is y tends to -5, limit as y approaches -5 and the function is y square over y minus 5. This is also a rational function where if we substitute -5 for y, the denominator does not become 0. So the usual stuff. Sometimes when we keep on solving this type of exercises, we get used to the things so much that we start taking our guards down, if I say so. And that is the point we start making mistakes. Okay, no matter how trivial, how easy something may look like, whenever you are doing something, no, it should not, at least in mathematics, it should not be a second nature that you are doing things, you are going on doing something absent-mindedly and you don't even notice that you have done something wrong. Always, no matter what you do, you think what you are doing. Okay, so that will save you from many mistakes which otherwise are easily overlooked. So because substitution is no problem, so we do that. And what are we getting? 25 in the numerator and -10 in the denominator. After cancelling common factors, we are left with -5/2. So that is the answer. Next, 10, limit y tends to 2 and the function is y plus 2 over y square plus 5y plus 6. Okay, here also a rational function, and if we put y equal to 2, the denominator does not become 0. That you can just simply say even without calculating the actual value. That's because you are putting a positive value and this cannot possibly be 0. Everything is, all the terms are going to be positive. So that's why the denominator is non-zero. To find the actual value, of course, we will have to know what this becomes. Y square plus 5y plus 6. So this gives us what? 2 plus 2 over 2 square plus 5 times 2 plus 6. So 4 plus 6 is 10, another 10, so 20 in the denominator, and in the numerator 4. So that means after cancellation you get the answer 1/5, 1 divided by 5. Okay, then 11, limit, and no need to modify this, let's just erase everything. So the next one is limit of 3 times 2x minus 1 whole square. Okay, limit of 3 times 2x minus 1 whole square. As the independent variable is approaching minus 1. This is not even a well, it is a rational function, but in particular it's even easier. It's a we are back with a polynomial function. So that's why, without even having that problem of having zero denominator, possibly you can just simply substitute. Okay, so minus 2 minus 1 is minus 3, and square of minus 3 is 9. So this is 9 times 3 is 27. 12. Limit x tends to minus 4. Okay, and the function is x plus 3 to the 1984th power. 1980, okay, that just looks like a year. That is my birth year, by the way, 1984. So we have, this is also a polynomial. Well, you can imagine that if you really want to write it as a polynomial, it will be extremely large, extremely long, because you have 1984, but after all it will become a polynomial. So that advice that I gave you just now, a little while ago, well, if you want, you can expand this using the binomial theorem if you know that. But there is no need actually. In this form itself, you can put x equal to minus 4, because after all it's a polynomial. That's why. I hope this is 1984 and not something else. But anyway, I have already said this, and I mean it is for every video. If you come across some mistake, please write in the comment section below so that we can rectify it together. Mistakes are, of course, inevitable. Since 1984 is an even integer, so it is 1. 13. The 13th one is limit y tends to minus 3, and the function is 5 minus y to the power 4 over 3. Well, here you can of course ask that this is not a polynomial. It's not, because you have a power where the exponent is a non-integer. It is positive, but it's a rational number that is not an integer. But from the graph of this function, you can of course conclude this, like what we did previously also with many functions. had we I mean, if we had only 4 here, say, that would have been a polynomial, but we have 4 over 3. 5 minus minus 3 to this power. So this becomes 5 plus 3, 8. Okay. The answer, however, can be simplified. The real cube root of 8 is 2 because 2 cube is 8. So that's why it becomes 2 to the power 4. That is, the final answer is 16. And if you are still wondering what we did in this step is justified once you draw the graph of this in a graphing calculator, and there you see what happens to the y values of the function. Well, here I should not say y value, because what happens to the output values of the function. The independent variable itself is y. As the independent variable approaches minus 3, you will see that the functional values approach 60. That's why. So that will justify this calculation also. Okay, the next 14. And the 14th one we have limit z tends to 0 of 2z minus 8, or if you want you can call it z also, whatever you prefer, with this exponent. This is the power. Here also same justification from the graph we have. Note that this is not square root, so we do not have any problem in spite of having a negative sign here. Minus 8 does have a real negative, a real cube root, and that cube root is minus 2, because if you take the cube of minus 2 is minus 8. That's why. Okay, so minus 2 is the answer. Next, 15. Here we have limit as h tends to 0 of 3 over square root of 3h plus 1 plus 1. Yes. I think I am running out of ink. Let me just, although I have to solve only one more, but still, if I run out of it completely, then it will take some time for the ink to again come back. Is there any problem in substituting 0? No. The denominator does not become 0, so we can just do that. Well, we can do that, but what is the justification? You see, we have already seen the limit laws. One of the limit laws tells us that this limit can be calculated to be equal to the limit of 3 as h tends to 0 divided by the limit of this as h tends to 0. The fact that in that denominator limit you can substitute 0 in place of h itself is justified by the graph of this denominator only. If you draw that as a function of h and then see what is happening to the graph as h is approaching 0, you will see that whatever we are going to write in place of the limit, that is if you substitute h equal to 0, is justified. Okay. And because the numerator 3 remains 3 regardless of what happens to h, because it's a constant function, so the limit is also 3, and that's why we have this. So I am skipping steps. Ideally I should have written if this is equal to limit of 3 divided by limit of this, which I am not doing. And on top of that I am directly writing just this. So the final answer is just 3 over 2. And finally, let's see the 16th one. It's also another such. Five over square root of 5h plus 4 and along with that we have plus 2. Here also same justification, same logic. Okay, now for this last one means last one for today. Let me just add that missing step. Just to say something after I complete the solution about this type of things. Okay, 5 is constant, so the numerator is 5 and the denominator, just like the previous one, is this. It approaches 5 times 0 plus 4, its square root plus 2. So that means square root of 4, that is 2, because this is a non-negative square root. 2 plus 2 is 4. So we get 5 over 4 as our final answer. Now what I want to say at this point is this. See, we are calculating many things, many limits, right? But so far we have got only an informal definition of limit, which is just this. You have a function. In a function, of course, what is it that you have? You have an independent variable, and the function tells you that when you have an independent variable, then what the value of the dependent variable is for that particular value of the independent variable, and that the function does by giving you a formula, and we are using these formulas to calculate the limits of the functions as the independent variable approaches something. So the definition of limit so far is informal because we are being somewhat vague when we are saying that, for example, this is your function here the independent variable is h, and for h the value of the dependent variable is this. Now as h is nearing 0, either from the left hand side of 0 or from the right hand side, we are considering both sides. Then what is happening to these values? These values are approaching 5/4. To justify that even more, or rather strictly speaking in a slightly different way, we are taking the help of graphs of these functions. But still, actually what we are saying is extremely vague. It's not mathematical. It is just simply a way of saying that if I go there, then something will happen. Okay, it's as vague as that. So far we haven't got any, what can I say? We are going to get that in the next few sections, the actual mathematical definition of limit. But until we get that, these calculations, truly speaking, are not justified. We can say however many times we want that from the graphs of these functions we can see that this denominator is approaching 4, for example, but that is not a mathematically rigorous justification. And we are unable to give a rigorous justification because we do not have a rigorous definition of limit so far yet. In other words, we just have a vague idea of what limit should be, but we actually still do not know what limit is truly. We are going to get to that. But even when you get the actual definition of limit, that there is no lack of rigor in that definition. That is, in fact, when you get that, you will see that that is the actual definition of limit, which has no gaps. But still, the aim of calculus is not looking into all the nitty-gritties and all the minute details of these things, but the aim is to get us to do the calculations, to get the answers. If you want to really sit down and think about these things and analyze all the details minutely, for that you have to go to a higher level course, which are there. Real analysis is one such thing, where we investigate the reasons for which these things are true. So there is time for that. That is why right now everything will not be clear. It's the job of calculus to make the things as clear as possible so that we don't make mistakes, but everything cannot be justified fully at this stage. So that will only come next when the time comes. That is beyond calculus. Okay, when we get to real analysis, there only we can justify all the things. So for that we have to wait. Right now we just need to see what the things are and roughly how the calculations go. So with this I want to end the video tonight, and tomorrow of course again we have our upload, and tomorrow we are going to solve ring theory problems from Galilean. So see you tomorrow with that. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.